A fire progress in four steps: ignition, flame spread, flashover, and consumption. The first stage of any fire begins with the ignition of a fuel source. Ignition requires the proper blend of oxygen, heat, and fuel. The second stage is the flame spread, which is characteristic of rapid crawling tongues of fire that leaks across the surface of walls, ceilings, floors, and supporting timbers. The nature and combustibility of the material govern the speed and the intensity of flame spread. As the fire intensifies, the heat material releases large volumes of volatile gases into the air. When the mixture of gases and air reach critical proportions, the material ignites in a great ball of fire, called the flashover stage. Flashover instantly consumes the surrounding oxygen and can raise the premise temperature to exceed 1500 degrees Fahrenheit or 816 degrees Celsius. During the flashover stage, the fire might reach explosive proportion. The final stage in burning sequence is the fiery consumption of the material itself as it burns to ash. The rate of destruction depends on the amount of oxygen-rich air reaching the burning area and the combustibility of the fully ignited material. Generally, fire are classified into four groups by type of fuel. Group A: ordinary combustibles. For example, wood, paper, plastics, trash, grass, and so on. Group B: flammable liquids. Gasoline, oil, grease, acetone, and so on. Group C: electrical equipments. Any electrical wiring connections, equipment, and so on. Group D: combustible metals. Potassium, sodium, aluminum, magnesium, and so on. Extinguishing fire. Building fires typically begin with the ignition of a building contents. If the flames are not extinguished quickly, the fire will expand throughout the structure. Fire will spread throughout concealed spaces and cavities in walls, floors, crawl space, and attic, and eventually to the outside of the building. Once ignited, fires become self-sustaining as the increase in temperature heats the fuel above its flash point. Fire must be extinguished by eliminating at least one of the constituents in the chemical reaction: fuel, oxygen, or heat energy. Taking away the fuel, cutting the oxygen supply, and lowering the temperature of the burning mass and surroundings are the effective methods. Extinguishing a building fire is more complex than quenching a contained fire. The spreading flames that are sometimes concealed must be located and disrupted in addition to extinguishing the original contained fire. To accomplish this effectively, the firefighter must know the various ways fire can spread throughout a building structure. Building materials exposed to the high temperature in a fire can fail rapidly. Structural collapse from high temperature is a real safety concern in building. The materials most commonly used in building structural assemblies are steel, wood, brick, and concrete. Their performance in a fire varies significantly. Steel. Steel is a non-combustible material, yet it displays a significant loss in strength at high temperatures. Structural steel loses about half of its strength at a temperature about 950 degrees Fahrenheit or 510 degrees Celsius. At temperatures of about 1350 degrees Fahrenheit or 730 degrees Celsius, steel loses about 90% of its strength. As a result, structural steel is typically protected from fire by an insulating layer of fire-resisting material. A fire-resisting material limits temperature rise of steel in a fire to keep it from losing strength. Stronger materials such as concrete or masonry may also contribute to the load carrying capacity of the assembly, thus extending in some cases the fire endurance. Lumber and timber. Wood is a good insulator, but when it is exposed to fire at temperatures as low as 300 degrees Fahrenheit or 150 degrees Celsius, it will burn until it is destroyed. In a fire, wood loses strength by charring. The reduction in effective cross-sectional area is dependent on the number of faces exposed to the fire. The penetration of surface charring of the wood surface in a fire is fairly consistent with time. Brick and other fired clay products are vitrified in a kiln or oven at high temperatures during their manufacture. As a result, fired clay masonry units are relatively stable in a fire endurance test. Brick also displays reasonably good thermal performance. One of the more significant factors in the fire endurance of hollow brick masonry is the amount of solid material in the wall thickness. Hollow clay masonry units have the thin face shells and webs are subject to stresses resulting from unevenly distributed thermal expansion. The tendency of spalling and shattering has been observed in hollow clay tiles. Concrete. Concrete, which is similar to brick in thermal performance, loses strength gradually during the exposure to high temperature. It retains about half its original strength at 950 degrees Fahrenheit or 510 degrees Celsius, and one-third of its original strength at about 1300 degrees Fahrenheit or 700 degrees Celsius. This loss in strength is irreversible because it is from the deterioration of the cement binder and in some cases the degradation of the aggregate. The fire endurance properties of concrete depend on the type of aggregate, the proportion of the concrete mix, and the moisture content at the time of the fire exposed. There are 5 fundamental categories of building construction in the United States, known as the types of building construction. Each type of building construction has fire-resistive strengths and weaknesses. That is, some types burn much more rapidly than others. The table shows the types of building construction that serves as the fundamental categories of building construction in the United States. Fire-resistive construction is built with its concrete and protected steel walls, floors, and structural framework. Was initially intended to confine a fire by its method of construction, that is, by containing the fire with non-combustible wall, ceiling, and floor assemblies, so it is confined to one floor or one space on a floor. However, fire does spread several floors in a modern fire-resistive building through 2 paths: through ductwork in the central heating, ventilating, and air conditioning system, and by flames extending vertically from window to window. Deadly smoke can be distributed throughout the building. Therefore, the first action taken in a burning fire-resistant building should be to shut down the HVAC air system. The vertical spread of flames from windows below to windows above is another way of fire spread throughout a Type 1 building. Flames erupting out of a heat-shattered window can break or melt glass in a window directly above. Once the window above is open, flames can enter and ignite combustible ceiling tile, wall hangings, or furnishing. Even if the windows do not melt or break from heat, concealed cavities between the exterior wall and the end of floor slab can allow the vertical spread of fire and smoke from floor to floor above and near a window. Non-combustible construction, or Type 2. Non-combustible construction is also built of non-combustible steel or concrete walls, floors, and structural framework. However, the roof covering is combustible, which can be burned and spread fire. Combustible foams may be used as thermal insulation. When a fire occurs inside a Type 2 building, flames can rise to the underside of the steel roof deck, conduct heat through the metal, and ignite the combustible roof covering. The asphalt, felt paper, and foam insulation may burn and spread fine along the roof covering. Ordinary construction or Type 3. Ordinary construction is built of non-combustible masonry bearing walls, but the floors, structural framework, and roof can be made of wood or another combustible material. The, main, the major occurring fire spread problem with Type 3 construction is concealed spaces and penetration. These small voids, cavities, and openings through which smoke and fire can spread are found behind the partition walls, floors, and ceilings. Wood studs, floor joints, and suspended ceilings created concealed space. Flames can spread vertically several stories or horizontally to adjoining occupancies through concealed spaces. Fires spread inside concealed spaces of a Type 3 building by convection. The transfer of heat by motion of a liquid or gas, heated fire gases and flames in a concealed spaces can travel upwards several floors and break out in attic space, engulfing the entire building envelope. Type 4 construction or the heavy timber construction. Heavy type construction is built of a structure that consists of a large timbers. In this type of construction, a wood column cannot be less than 8 inches thick in any dimension, and a wood beam cannot be less than 6 inches thick. The floor and roof decking can be thick wood planks, exposed timber beams, columns, and decks. If ignited in a fire, create large radiated heat waves after the windows break during a blaze. If a fire in a heavy timber building is not extinguished by the initial firefighting attack, a tremendous fire with flames shooting out of the windows will spread fire to adjoining buildings by radiated heat. A fully involved Type 4 building requires large water supply sources to protect nearby buildings. Wood frame construction or Type 5. Wood frame construction is the most combustible of the 5 types of the building construction. A wood frame building is the only one of the 5 steps of the construction that has combustible exterior walls. The interior framing and the exterior walls are typically constructed of slender repetitive wood studs, joints, rafters, and trusses that burns rapidly. Flames can spread out a window and then along the outside wood walls in addition to the interior fire spread. A Type 5 building is rapidly engulfed in flame and is therefore reserved for small structures with small occupancies. Although heat alone can prove deadly to occupants, toxic gases and smoke cause the majority of deaths and injuries. About half of all fatalities from fires are from carbon monoxide poisoning, and more than a third are from cardiopulmonary complication. Fire is one of the greatest fears of any homeowner, business owner, or director of an institution. Although the prime concern is always loss of lives in a fire, more than half of all businesses never open after the devastating effect of fire. The threat of a fire destroying lives and property can be reduced tremendously by proper installation of fire detection alarms and suppression equipment. In residence, automatic sprinkler systems cut the chance of dying in a fire by more than half. When combined with smoke alarms, they cut the chances of dying in a fire by more than 80% relative to having ignited. Sprinklers also cut the average property loss in a fire by one half to two-thirds. There are fire protection measures that can be used to either prevent or at least reduce the impact of fire accident to buildings and humans. These fire protection measures are grouped into two, which are the passive and active fire protection. Passive fire protection. Passive fire protection in buildings involve constructing walls, floors, ceilings, beams, columns, and shaft enclosures so they can resist, control, and contain the damaging effect of a fire. It is intended to entail the following: provide structural and thermal integrity of floor, wall, and ceiling assemblies during a fire for a specified time period. Compartmentalize a room or space to control fire spread. Provide exiting systems for occupants to safely and rapidly evacuate the building. If well designed and maintained properly, passive fire protection systems are extremely effective in protecting building occupants and controlling the spread of fire. These systems require periodic inspection and necessary maintenance. Breaches in structural and thermal integrity caused by renovation can lead to lack of proper protection in a fire emergency situation. Passive fire protection includes the following subtopics: fire-resistant construction, fire-protective materials, fire doors and windows, fire and smoke dampers, fire and smoke ratings. Example of passive fire protection measures that are evident in most public buildings will be discussed furthermore as we continue our discussion. Active fire protection and suppression. Active fire protection systems include standpipe, sprinkler, and spray systems designed to extinguish the fire outright or control the fire by delaying its damaging effects. Types of firefighting media include water, foams, inert gases, and chemical powders. Active fire protection systems are extremely effective in containing and fighting a fire if they are designed and maintained to work properly. These systems require regular inspection, testing, and maintenance. Poor maintenance leads to a false sense of security and lack of proper protection when the system is needed under an emergency situation.
Passive fire protection. Passive fire protection in buildings involves constructing walls, floors, ceilings, beams, columns, and shaft enclosures so they can resist, control, and contain the damaging effects of a fire. It is intended to entail the following: provide structural and thermal integrity of floor, wall, and ceiling assemblies during a fire for a specified time period. Compartmentalize a room or space to control the fire spread. Provide exiting systems for occupants to safely and rapidly evacuate the building. If well designed and maintained properly, passive fire protection systems are extremely effective in protecting building occupants and controlling the spread of fire. These systems require periodic inspection and necessary maintenance. Breaches in structural and thermal integrity caused by renovation can lead to lack of proper protection in a fire emergency situation. A principal objective of fire-resistive construction is to use materials and construction assemblies that contain the fire in a small area and confine the fire in the room or area for a specific period of time. Fire-resistive construction includes compartmentalizing, fire walls, fire separation, and fire stop. Compartmentalizing means separating a building into compartments so that if there is a fire, the fire damage is confined to certain a room or certain section of the building only. Fire walls are fire-rated walls that form a required barrier to restrict the spread of fire throughout the building. It serves as a means of dividing a large structure into compartments. They are normally built of brick, concrete, or masonry. Typically, it must extend from the foundation and intersect a non-combustible roof surface or extend beyond the roof by a specified vertical distance, usually 32 inches or 813 millimeters. Fire separation is similar to a firewall except that it does not extend from the foundation to the roof assembly. It is used to divide different occupancies in a building, for example, a garage from a residence, or enclose exit corridors and stairs. A shaft wall is a protective fire-rated enclosure around an elevator hoistway or mechanical chase. It is a specific construction technique consisting of all materials that fill the opening around penetrating items such as cables, cable trays, conduits, ducts, and pipes and their means of support through the wall or floor to prevent the spread of fire protective materials. Several site-applied fire protective coverings, insulations, and coatings can be used to insulate structural members from the effects of high temperatures generated in fire. The performance of these insulations is dependent on the thickness. A thicker material provides greater fire resistance. Some examples of fire protective materials that are commonly used are gypsum wallboard, rock wool, vermiculite, concrete and masonry. And intumescent material. Gypsum wallboard is a fire protective covering that consists of approximately 21% water chemically bonded to calcium sulfate. In a fire, a large amount of energy is released to evaporate water in the gypsum material, giving it excellent fire protective qualities. Rock wool is a fibrous insulation made from volcanic rock. It is melted and spun into fibers to create the insulation. Vermiculite is a material that has a low density and good insulation properties used in building boards. These boards are often used as a core in fire doors to build fire barriers, to encase or construct ductwork and to protect steel building materials from the effects of fire. Concrete and masonry is widely specified for fire walls and fire barriers because it is non-combustible, provides durable fire resistance, and is economical to construct. The last example of fire protective materials is intumescent material. These materials swells, enlarges, inflates, and expands when exposed to heat. Fire protective intumescent coatings are applied like paint to structural steel members at a thickness that ranges from 0.03 to 0.4 inches, or 0.8 to 10 millimeters. These intumescent coatings expand approximately 15 to 30 times their volume when exposed to high temperatures in a fire, and thus provide a good fire protective barrier. Fire doors and windows. Fire doors are typically of steel or solid wood construction and are installed with specially tested components including closers, latching hardware, and fire-rated glass lights, windows. Intumescent seals are fitted to the edge of the door leaf or in the frame reveal. An intumescent seal expands in fire to seal the gap between the edge of the leaf and the frame, as a result preventing the passage of smoke and flame. There are two categories of fire-resistant glass. First is the insulating glass and the other is the transmitting glass. Insulating glass contains flames and inflammable gas for a longer period of time and prevents not only the transmission of flames and smoke but also of heat to the other side of glazing. On the other hand, transmitting glass contains flames and inflammable gas for a short period of time, but does not prevent the transmission of heat to the other side of the glazing. Examples of this are wired glass and reinforced laminated glass. Fire and smoke dampers. Fire dampers automatically close to obstruct smoke and fire from a building blaze. Fire dampers are installed in the plane of the firewall to protect these openings. Upon detection of heat, the fusible link, available in 165 degrees Fahrenheit, 212 degrees Fahrenheit, and 285 degrees Fahrenheit, melts, closing the fire damper blades and blocking the flame from penetrating the partition into the adjoining compartment. Smoke dampers, on the other hand, close upon detection of smoke, preventing the circulation of air and smoke through a duct or a ventilation opening. They can be part of an engineered smoke control system designed to control smoke migration using walls and floors as barriers to create pressure differences. Pressurizing the areas surrounding the fire prevents the spread of smoke into other areas. They are controlled by a smoke or heat detector signal that is part of a fire alarm control system. Fire and smoke ratings. Several fire and smoke ratings are used to classify the behavior and performance in a fire. Common ratings include the following: fire resistance ratings, flame spread ratings, Class ABC roof coverings. Smoke developed rating. Fire resistance ratings are expressed in hours or minutes. It is a measure of fire endurance, the elapsed time during which a material or assembly continues to exhibit fire resistance under specified conditions. Assigned to building assemblies, walls, columns, girders, beams, and composite assemblies for ceilings, floors, and roofs. based on results from laboratory testing that determine their ability to withstand the effects of a fire for a period of time. Table 21.2 shows the fire resistance ratings of selected construction assemblies compiled from various industry sources. The first column consists of the fire resistive rating, and corresponding to each of them are the basic description of construction assembly. This table includes the fire resistive rating for walls and or partitions, floors and or ceilings, steel columns, and doors, which include fire door, frame, hardware, and other accessories. For walls and partitions, the rating includes 1 hour, 2 hours, 3 hours and 4 hours depending on the construction assembly. For floors and ceilings, the ratings are 1 hour and 2 hours. For steel columns, the ratings are 1 hour, 2 hours, and 3 hours. For doors, specifically steel doors, the ratings are 3 hours, 1.5 hour, 3/4 hour, and 20 minutes. For wood doors, the ratings are 90 minutes, 60 minutes, 45 minutes, and 20 minutes. Other assemblies, like horizontal assemblies, partitions, and exterior walls, require only part or parts to have a fire resistance rating. Horizontal assemblies, for example floors, ceilings, roofs, are tested for fire exposure from the underside only because a fire in the compartment below presents the most severe threat. Partitions, interior non-load bearing walls, required to have a fire resistance rating equally from each side because a fire could develop on either side of the fire separation. Exterior walls only require a rating for fire exposure from within a building because fire exposure from the exterior of a building is unlikely to be as severe as that from a fire in an interior room or compartment. Another rating is the flame spread ratings. The flame spread rating, FSR, describes the surface burning characteristics of a building material. The most widely accepted flame spread classification system is specified in the National Fire Protection Association, NFPA, Life Safety Code. The FSR is expressed as a number on a continuous scale wherein organic reinforced cement board is 0 and red oak is 100. The scale is divided into 3 classes. The NFPA Life Safety Code groups the following classes in accordance with their flame spread and smoke development based on classes A, B, and C. In the table, Class A has a flame spread of 0 to 25 and is said to have a good resistance. Class B has a flame spread of 26 to 75 and has a fair resistance, and Class C has a flame resistance of 76 to 200 and has a poor resistance. The FSR is specific to a particular surface and substrate. Other aspects of the wall or ceiling structure do not affect these surface burning characteristics. However, painting the surface changes the surface burning characteristics. For this reason, special care must be exercised in determining the type and thickness of paint applied to Class A surfaces because the FSR can be changed. Table 21.3 shows the flame spread ratings and classifications for common materials compiled from various industry sources. Column 1 contains the material or species, flame spread rating in column 2, and flame spread class in column 3. Moreover, Table 21.4 shows the flame spread classifications for common siding and sheathing materials compiled from various industry sources. Column 1 contains the material, flame spread class in column 2, and typical use, whether for siding or sheathing, in column 3. Another rating is the Class ABC roof coverings, which is sometimes confused with the Class ABC flame spread categories mentioned previously. But the two ratings are different. This roof covering rating has no correlation with Class ABC flame spread categories. The roof covering classification test is a pass-fail test under which a product either passes the criteria as a Class A, B, or C roof covering system or it does not. The highest classification for a roof covering is Class A and Class C is the lowest. The last rating is the smoke developed rating. It is a single number classification of a building material as determined by an ASTM E84 test of its surface burning characteristics. It is expressed as a ratio of the smoke emitted by a burning material to the smoke emitted by the red oak standard material.
So now, we are down to tackle the fire protection systems, its types, classifications, and components. Fire suppression systems are intended to extinguish or control a fire. These include automatic water sprinkler systems and extinguisher systems that use a gas agent or foam to eliminate oxygen and suffocate the fire. A fire extinguisher is an active fire protection device used to extinguish or control fires. Now, here are the components of portable fire extinguishers. 1 is the cylindrical tank. It is the largest and the most recognizable component of a fire extinguisher is certainly the red cylindrical tank that houses the chemicals used to put out fires. Note that not all fire extinguishers are red, but they tend to be. The cylindrical tank has a flat bottom, so that the extinguisher can be placed on the floor, and a top shaped like a dome. The propellant and the extinguishing agent are inside this tank. The tank is made of metal. 2. The valve assembly. Valve assembly regulates and controls the flow of the extinguishing agent inside the tank. This component of a fire extinguisher is comprised of several subcomponents. These are the 1. The body. The machined body of the valve assembly is usually made of a metal bar shaped by a lathe. The body of the valve assembly on some lower-end fire extinguishers is made of injection molded plastic. 2. The handle. The handle allows you to pick the extinguisher up and carry it to the place affected by the fire. 3. The pull pin. The pull pin prevents accidental discharge of the extinguishing agent. You first have to remove the pull pin before you can actually use the fire extinguisher. 4. The tamper seals. Tamper seals are made of plastic, and they keep the pull pin in place. 5. The release lever. Pressing the release lever allows the extinguishing agent to begin discharging. 6. The dip tube. This tube goes inside the cylinder tank and it draws the agent up when you press the release lever. 7. The pressure gauge. Stored pressure extinguishers contain a gauge that measures the pressure of the chemicals hosted within the tank. Another valve assembly component are the nozzle and hose. These two components direct the extinguishing agent as it starts leaving the cylinder tank. Some extinguishers do not have a hose, and they only employ a nozzle to distribute the extinguishing agent. However, fire extinguishers that exceed 5 pounds in weight typically tend to have a hose as well, as it allows you to change the direction of the flow more easily. Fourth component is the extinguishing agent. The extinguishing agent is a vital component. This chemical substance is what actually suppresses or puts out the fire. Depending on the class of a fire extinguisher, the type of the extinguishing agent will vary. Some extinguishing agents are suitable for taking out electrical fires, while others work better for combustible and flammable liquids. Consequently, the extinguishing agent can be dry chemical monoammonium phosphate, or a blend of potassium acetate and potassium citrate. Another component is the propellant. Propellant is a gas that expels the extinguishing agent from the extinguisher. Depending on the type of fire extinguisher, the propellant has a different location. First is the stored pressure extinguishers house the propellant together with the extinguishing agent. Second is the cartridge-operated extinguishers store the propellant within a separate cartridge. When you activate the fire extinguisher, this cartridge gets punctured to provide the necessary pressure for the extinguishing agent. Here is a sample photo to show fire extinguisher components. Now we are down to the classifications of portable fire extinguishers. Portable fire extinguishers are classified according to their ability to handle specific classes and sizes of fires. Not all fuels are the same, and if a fire extinguisher is used on the wrong type of fuel, it can make matters worse. Class A extinguishers. Class A extinguishers are suitable for use on fires in ordinary combustibles such as wood, paper, rubber, trash, and many plastics, where a quenching cooling effect is required. The numeral indicates the relative fire extinguishing effectiveness of each unit. Class A extinguishers are rated from 1A to 40A. Extinguishers rated for Class A hazards are water, foam, and multi-purpose dry chemical types. Class B extinguishers. Class B extinguishers are suitable for use on fires in flammable liquids, gases, and greases, where an oxygen exclusion or flame interruption effect is essential. Class B extinguishers are rated from 1B to 640B. A discussion follows. Extinguishers rated for Class B hazards are foam, halon alternative, and CO2 and multi-purpose dry chemical. Class C extinguishers. Class C extinguishers are suitable for use on fires involving energized electrical equipment and wiring where the dielectric conductivity of the extinguishing agent is of importance. For example, water solution extinguishers cannot be used on electrical fires because water conducts electricity and the operator could receive a shock from energized electrical equipment via the water. Class D extinguishers. Class D extinguishers are suitable for use on fires in combustible metals such as magnesium, titanium, zirconium, sodium, and potassium. No numeral is used for Class D extinguishers. The relative effectiveness of these extinguishers for use on specific combustible metal fires is detailed on the extinguisher nameplate. Here is a picture showing what classification and type of extinguisher allowed to be used. Now let us proceed to the types of portable fire extinguishers. Fire extinguishers may contain mixtures of water, but they are also available with gases or dry chemicals. Some of the common types of fire extinguishers are as follows. First is the air pressurized water fire extinguishers. Air pressurized water, APW, extinguishers are large, silver tanks filled about 2/3 water, and then pressurized with air. An APW is a giant squirt gun that stands about 2 feet tall and weighs approximately 25 pounds when full. They are designed for Class A fires only, solid combustible materials that are not metals such as wood, paper, cloth, trash, and plastics. Second is the carbon dioxide fire extinguishers. Carbon dioxide, CO2, fire extinguishers are filled with non-flammable carbon dioxide gas under extreme pressure. They are designed for Class B and C fires only, flammable liquid and electrical. CO2 is a gas that extinguishes fire by displacing oxygen. CO2 is also very cold as it comes out of the extinguisher, so it also cools the fuel. CO2 may be ineffective at extinguishing Class A fires because they may not be able to displace enough oxygen to successfully put the fire out. Burning materials may smolder and reignite. CO2 extinguishers are used in laboratories, mechanical rooms, kitchens, and flammable liquid storage areas. CO2 extinguishers are filled with non-flammable CO2 gas under extreme pressure. A CO2 extinguisher can be recognized by its hard horn and lack of pressure gauge. CO2 cylinders are red and range in size from 5 pounds to 100 pounds or larger. In the larger sizes, the hard horn will be located on the end of a long, flexible hose. Third is the dry chemical fire extinguishers. Dry chemical fire extinguishers put out fire by coating the fuel with a thin layer of dust, separating the fuel from oxygen in the air. The powder also works to interrupt the chemical reaction of fire, so these extinguishers are extremely effective at putting out fire. Dry chemical extinguishers come in a variety of types. ABC indicates that they are designed to extinguish Class A, B, and C fires. BC indicates that they are designed to extinguish Class B and C fires. Class ABC fire extinguishers are considered multi-purpose. They are usually filled with ammonium phosphate. They are not ideal for electrical fires because they leave a hard residue that is difficult to remove. Class ABC fire extinguishers are found in a variety of locations. New buildings will have them located in public hallways. They may also be found in laboratories, mechanical rooms, break rooms, chemical storage areas, offices, and vehicles. ABC extinguishers are red and typically range in size from 5 pounds to 20 pounds. Class BC extinguishers may be located in places such as commercial kitchens or areas with flammable liquids. Location and proper care of fire extinguishers should always be considered. Portable fire extinguishers must be located with the travel distance not more than 75 feet for Class A and Class D hazard areas, and not more than 50 feet for Class B hazard areas. Extinguishers should be located outside the door/accessible area. Extinguishers must not be blocked or hidden by stock, material, or machines. It should be kept clean and should not be painted in any way that could camouflage them or obscure labels and markings. Now we are bound to the next system, the sprinkler system. Automatic fire suppression systems are intended to extinguish or control a fire. These include automatic water sprinkler systems and systems that use a gas agent or foam to eliminate oxygen and suffocate the fire. An automatic sprinkler system consists of the sprinkler heads and a network of pipes placed in a horizontal pattern near the ceiling and is designed to automatically dispense water on a fire. A conventional sprinkler system is fitted with automatic devices designed to release water on a fire. These devices are called sprinkler heads. A rise to a predetermined temperature causes the sprinkler head to open. Water is then discharged in the form of spray. When the sprinkler heads open, they are said to have fused. The sprinkler heads are fitted at standard intervals on the piping. If more than one head opens, the area sprayed by each overlaps that of the sprinkler head next to it. Here are the types of conventional automatic sprinkler systems. First type is the wet pipe automatic sprinkler systems. Wet pipe automatic sprinkler systems have pressurized water in the pipe and mains. Water is released when the sprinkler head is activated. Because of the potential for freezing, this system is suitable for buildings where the indoor ambient temperature is not lower than about 40 degrees Fahrenheit 5 degrees Celsius. Wet pipe sprinkler systems are the most common in use today. In wet systems exposed to freezing temperatures, pipes containing an antifreeze solution of water, glycerin or water, propylene glycol are connected to a water supply. The antifreeze solution, followed by water, discharges from sprinkler heads opened by a fire. This type of system is used in locations subject to freezing. Use of antifreeze solutions is limited because they are costly and are difficult to maintain. Figure 21.2 shows a schematic drawing of a wet pipe sprinkler system. Second type is the dry pipe automatic sprinkler systems. Dry pipe automatic sprinkler systems have pipes filled with compressed air or nitrogen. The pressure in these lines is slightly above the water pressure, and this pressure difference is what keeps the water out of the sprinkler lines. When a sprinkler head is activated, the air will begin to be released and the air pressure will drop. As air pressure drops, water will begin to advance throughout the lines and flow through the activated head. The dry pipe type is typically used in unheated buildings where there is danger that the water in the pipes would freeze and burst the pipes. Third type is the pre-action automatic sprinkler systems. Pre-action automatic sprinkler systems are similar to dry pipe except that the water first fills the pipe as an alarm is set off, providing an opportunity to extinguish the fire manually before the sprinklers open. Water is stopped at feeders, in the walls before the pipes supplying the sprinkler heads, by a valve. This valve is electronically activated by a heat detecting device within the area, and a signal is sent to the valve and the valve opens. Water will then flow to all heads, but will only discharge through the activated heads. If there is an accidental break of a sprinkler line, water will not immediately discharge because the valve is holding back the water flow and not the sprinkler heads, unlike the wet pipe or dry pipe systems. The pre-action sprinkler system is often used where the use of sprinklers could cause extensive material or equipment damage, such as in retail stores and computer areas. Fourth type is the deluge automatic sprinkler systems. Deluge automatic sprinkler systems allow all sprinkler heads to go off at the same time. This system is very similar to the pre-action system, except all sprinkler heads are open. Once a heat detecting device activates the valve, water will flow from all heads within the area. Deluge systems are generally installed in hazardous areas where extremely rapid fire spread is anticipated and that requires immediate application of water. Automatic sprinklers are devices that open automatically to discharge water when an excessive temperature is detected. Each sprinkler is typically individually heat activated. When the heat of a fire raises the sprinkler temperature to its operating point, example 165° F/75° C, a solder link will melt or a liquid-filled glass bulb will shatter to open that single sprinkler. Once the sprinkler is open, water from the sprinkler pipes flows directly over the source of the heat, as shown in figure 21.3. The system works immediately upon sensing excessive temperature to prevent the fast-developing fires of intense heat, which are capable of trapping and killing building occupants. Sprinkler heads are made of metal. They are screwed into the piping at standard intervals. Water contained within the system is prevented from leaving the sprinkler head by an arrangement of levers and links. The levers and links are soldered together on the sprinkler head. The solder is a metal alloy with a fixed melting point. Some sprinkler heads are designed for special situations. Sprinkler heads exposed to corrosive conditions are often covered with a protective coat of wax or lead. Corrosive vapors are likely to make automatic sprinklers inoperative or slow down the speed of operation. They can also seriously block the spray nozzles in the sprinkler heads. They can damage, weaken, or destroy the delicate parts of the sprinkler heads. In most cases such corrosive action takes place over a long time, so sprinkler heads must be carefully monitored for signs of corrosion. Care must be taken to ensure that the protective coating is not damaged when handling or replacing the heads. Operation and layout must also be considered in installing sprinklers. In conventional systems, individual fire sprinklers are spaced throughout the ceiling of a building at predetermined intervals or positions. Most sprinklers have a 1-2 in discharge opening. Each sprinkler can cover approximately 100 square feet. Sprinkler heads are usually positioned upright, pendant, pointing downward, or sidewall, pointing sideways. A network of pipe delivers water to the sprinkler heads. Types of pipe approved for use include the following. The steel pipe are approved for use in all fire suppression sprinkler applications. It is available in the following nominal diameters: 3/8, 1/2, 3/4, 1, 11.4, 11.2, 2, 21.2, 3, 31.2, 4, 5, 6, 8, 10, and 12 inches. Threaded and flanged connections are used to join pipes and fittings. Specialty compression strap type fittings, called Victaulic couplings, make system installation easier. Copper tubing is the most popular water supply pipe material, but it is used less frequently in fire sprinkler systems. The thin walls of copper tubing are usually soldered to fittings. It is available in the following nominal diameters: 3/8, 1/2, 3/4, 1, 11/4, 11/2, 2, 21/2, 3, 31/2, 4, 5, 6, and 8 inches. Chlorinated polyvinyl chloride, or CPVC, is a rigid plastic pipe generally approved for use in fire suppression sprinkler systems in residential and many light commercial applications. It is available in straight lengths in the following nominal diameters: 1, 11/4, 11/2, 2, 21/2, 3, 31/2, 4, 5, 6, 8, and 10 inches. Solvent cement welding, threaded, and flanged connections are used to join CPVC pipe and fittings. CPVC pipe and fittings for fire sprinkler systems are orange in color. Alarm and control valves. An alarm valve and gate valve are important. It serves to control flow in the network of sprinkler system. The alarm valve initiates an alarm signal when water flows through the sprinkler system. The gate valve opens or closes flow to the system. It should be maintained in the open position at all times. Large buildings must be protected by multiple sprinkler systems, each having an alarm valve and gate valve. The alarm valve and gate valve must be functioning in order for the system to work. Operation of the control valves can be accomplished by the automatic fire alarm system by provision of valve tamper switches that will initiate a trouble or supervisory signal at the fire alarm control panel to indicate a closed valve. If this type of monitoring cannot be provided, the valves should be locked in the open position. Here are the primary sources of water supply of sprinklers. Potential sources of water supply for sprinkler and standpipe systems include a direct connection to the public water system, gravity tank, pressure tank, or automatic fire pump. Where a municipal water supply cannot meet flow and pressure requirements, a reservoir or storage tank must be provided to provide a secure water supply. There is also a supplementary source of water supply of sprinklers. This include manually or automatically activated fire pumps or Siamese connections. Tanks used to provide the required primary water supply to a standpipe system may also be used as a supply for an automatic sprinkler system. A Siamese connection is a Y-shaped inlet connection for fire department use in supplementing or supplying water for standpipes and sprinkler systems. If a firefighting unit arriving at a fire finds that the sprinkler or standpipe systems is not receiving sufficient water and pressure, a fire truck pumper is connected to the sprinkler system to supply additional water. Siamese connections should be provided for all sprinkler and standpipe systems in commercial buildings. Fire sprinkler systems must also have backflow prevention capabilities installed to protect the public or private potable water distribution systems from backflow of water. The backflow prevention method required is dependent upon the hazard level or classification of the fire protection system. Typically, a double check valve assembly, DCVA, or a reduced pressure backflow prevention assembly, RBPA, is required in residential, commercial, and industrial installations. Sprinkler systems using secondary sources of water or that have chemicals added should be RBPA systems, while other systems can use the DCVA method. The backflow prevention assembly should be properly maintained, inspected, and tested annually by a licensed fire sprinkler contractor. Conventional sprinklers demand high water supply rates and are associated with fixed large diameter pipe networks around the area to be protected. The necessity for large amounts of water has some inherent disadvantages. It damages most of the building's contents and interior finishes. Flammable oils tend to float on the water's surface and continue to burn. It conducts electricity, and if it vaporizes into steam, it may be harmful to the firefighters. Therefore, an alternative fire suppression system is introduced. These are the following. First is the water mist automatic sprinkler systems. Water mist automatic sprinkler systems rely upon a fine spray of water to suppress a fire. A typical system consists of cylinders of water under pressure, heat/smoke detectors, and discharge nozzles connected to a network of pipes. The mist, with its small droplets of water, is very efficient in absorbing a large amount of heat as the droplets contact the fire and is converted to steam. This conversion to a vapor causes an expansion of over 1,600 times its original volume, thereby displacing oxygen and disrupting the combustion process. The small droplets affect heat transfer and tend to wet and cool combustibles much like a conventional sprinkler system. The optimum water droplet size ranges from 0.003 to 0.005 N, 80 to 200 m, although larger droplet sizes can be used. The nozzle design must produce a small droplet with an orifice sufficiently large to avoid clogging from suspended particulates that may be present in the water stream. When compared to conventional automatic sprinkler systems, the amount of water required in a water mist system is significantly less. Only very small amounts of water and air are needed to extinguish even the most intense fires, including gasoline fires, because a small amount of water is effectively spread into fine water droplets covering a large area. The principal advantages of a water mist system are that the small water droplets are not harmful to occupants, they are effective on flammable liquid fires, and they have minimal cleanup problems. This system is only permitted in a small number of applications. Second is the clean agent gas fire suppression systems. Clean agent gas fire suppression systems discharge as a gas on the surface of combusting materials. A typical system consists of cylinders of a liquid agent under high pressure, heat/smoke detectors, and discharge nozzles connected to a network of pipes. Large amounts of heat energy are absorbed from the surface of the burning material, lowering the surface temperature below the ignition point. Clean agent gases can be released in a building space without leaving residue. When released, they extinguish the fire rapidly but do little harm to building occupants, firefighters, interior contents, and equipment. Halogenated hydrocarbons, known as halons, have been used in clean agent gas fire suppression systems for decades. The most commonly used agent was halon 1301, an inert gas. However, because of its damaging effect on the Earth's ozone layer. Third is the carbon dioxide, CO2, fire suppression systems. Carbon dioxide, CO2, fire suppression systems discharge a CO2 gas that extinguishes fire by displacing oxygen or taking oxygen away from the fire. CO2 is also very cold as it comes out of the extinguisher, so it also cools the fuel. A typical system consists of cylinders of liquid CO2 under high pressure, heat/smoke detectors, and discharge nozzles connected to a network of pipes. CO2 are still the preferred agent in many confined space or tank applications. However, is usually used in confined areas such as mechanical chases, unventilated areas, and display cases. There are several common application systems that utilize CO2 to extinguish fires in engine compartments, dip tanks, and quench tanks, and operations where spilled fuel is a possibility. Fourth is the foam fire suppression systems. Foam fire suppression systems discharge a high volume of gas-filled bubbles that rapidly fill a space. Foam masses are lighter than water and flammable liquids, and they may be either air or chemical gas bubbles. They float on the surface of burning liquids to deplete oxygen and smother the fire. A typical system consists of foam generators, heat/smoke detectors, and a blower system that distributes the foam. Other systems discharge foam in a manner similar to a conventional sprinkler system. Foam is very effective on flammable liquid fires and most popular in areas where flammable fuel is likely to be, such as airplane or jet hangars. Here is an example of a diagram. A residential sprinkler system typically uses a 1-2 in, 12.7 mm, orifice, standard sprinkler, with a maximum of 256 square feet, 23.8 square meters, coverage, and a 25 GPM, 94.6 L/m, flow rate. If the system is not supplied by an adequate public water source, a 250 gal, 946.3 L, stored water supply is required to provide a 10 minutes water supply. Sprinklers are required in living rooms, bedrooms, or kitchen areas, but not required in bathrooms 40 square feet, 3.7 square meters, or less, small closets, 24 square feet, 2.2 square meters, or less, attics not used as a living space, porches, carports, garages, and foyers. A minimum 3/4 in water meter will be required to ensure adequate flow. The two most remote sprinklers in the structure must be designed to operate simultaneously, which usually adds a flow requirement of 16 to 20 gal/min, 65 to 75 L/min. Because multi-purpose systems are potable water systems, they eliminate the need for cross-connection control, that is, backflow prevention is not required. Now we are bound to tackle the third system, the standpipe system. A standpipe system is an internal piping network connected to fire hose stations that are used to rapidly suppress a fire. Firefighters can use hoses connected to the standpipe system or connect their hoses to valve outlets near the fire. Firefighters have great difficulty fighting fires from the ground when flames and smoke are visible above the fourth floor of a building. So, standpipe systems are mandated in buildings where it may be difficult for the fire department to adequately pump water on the fire, example in buildings that are over 6 stories or 75 feet in height. A standpipe system also provides water that trained occupants or employees can manually discharge through hoses until the fire department arrives. Piping in a standpipe system runs vertically, up and down, and horizontally, side to side, throughout the building. The standpipes running vertically are usually called risers. The risers are usually located in the staircase enclosures or in the hallways in the building. This piping system supplies water to every floor in the building. At selected locations in the building, the standpipe is connected to a hose. The hose is usually stored on a quick-release rack called a hose reel. Fire hose and reel stations are strategically positioned throughout the building. Gate valves control these connections. The occupant or firefighter must manually open the gate valve to open flow to the hose. A nozzle is attached at the end of the hose. The nozzle is used to direct the stream of water from the hose. The hose and nozzle must be easy to reach at all times. The hose outlets are located so that every part of the building may be reached with a hose stream. The maximum length of a single hose line is 125 feet. Sometimes the hoses are installed in cabinets. If the hose is installed in a cabinet, it must be labeled fire hose. Here are the types of standpipe systems. First type is the wet standpipe. This system always has water in the piping. The water in the system is always under pressure. In some cases a fire pump may be used to increase the water pressure. The wet pipe system is the most commonly used standpipe system. It is used in heated buildings where there is no danger of the water in the piping freezing. Any part of the standpipe system that is exposed to freezing temperatures should be insulated. It is very important that the water in the piping does not freeze. Frozen water may prevent a standpipe system from working. Second type is the dry standpipe with an automatic dry pipe valve. This system is usually supplied by a public water main. Under normal conditions there is no water in the piping. Instead, there is air under pressure in the piping. A dry pipe valve is installed to prevent water from entering the standpipe system. The dry pipe valve is designed to open when there is drop of air pressure in the standpipe. When a hose is opened it causes a drop in air pressure in the standpipe system. Then the dry pipe valve automatically lets water flow into the standpipe. A control valve is installed at the automatic water supply connection. This valve should be kept open at all times to supply the standpipe system. This system is usually installed in a building that is not heated. Third type is the dry standpipe with a manual control valve. This system is supplied by a public water main. Under normal conditions this system has no water in the piping. The water is not allowed into the standpipe until a control valve is manually operated. The control valve remains closed until a fire occurs. This system is usually used in a building that is not heated. The last type is the dry standpipe with no permanent water supply. Under normal conditions, this system has no water in the piping. Water is pumped into the standpipe system by the local fire department. The water is pumped in through the Siamese connection. See Siamese connection as follows. This system cannot be used unless water is supplied by the fire department. A sign must be attached to each of the hose outlets. It should read, "Dry standpipe for fire department use only." This system is usually used in a building that is not heated. Now here are the classification of standpipe systems. Standpipe systems are classified depending on who is expected to use the system. The three classes are briefly described in the following. Class I. This system is designed for use by professional firefighters. For example, fire department personnel use the system. The fire hoses in these systems are 21.2 inches in diameter. The large hose diameter makes it difficult to control the stream of water from the hose. Class II. This system is designed for use by the occupants of a building. The hose and nozzle are connected to the standpipe. They are ready to be used by occupants in case of a fire. The hose is 11.2 inches in diameter. The hose stream is easier to control than the Class I hose. Class III. This system may be used by either professional firefighters or by occupants of the building. The hosing may be adjusted to either 11.2 or 21.2 inches in diameter. Attaching special reducing valves to the hose line does this.
Fire detection and alarm systems. Fire alarm systems detect products of combustion such as smoke, heat, and light and provide early occupant notification. These systems use various methods to detect the products of combustion, including various heat and smoke detection techniques. They use audible and visual alarms to alert and warn building occupants. In a residence area, this system may be composed of a few standalone units. In large buildings, these systems include individual components such as smoke or heat detectors, control panels, fire command centers, communication centers, and alarm horns or speakers. Smoke alarms. It is a fire safety device that detects the products of combustion and gives off an audible and/or visual warning to building occupants. It is a smoke detector and alarm in one unit. Smoke alarms are powered by battery or are hardwired into the building electrical system with a battery backup. Smoke detectors. It is a sensing device that identifies products of combustion in air. Heat detectors. These are sensing devices that recognize a high temperature or a rapid increase in temperature. Various types of detectors. First, we have fixed temperature heat detectors. It signals an alarm after the temperature at the detector reaches a set value. Type of fixed temperature heat detectors are fusible alloy detectors. It employs metal alloys designed to rapidly melt at the desired temperature. We also have the bimetallic detectors. It uses sensing elements made of two strips of different metals, each having different thermal expansion coefficients. We also have the electrical conductivity detectors. These have a sensing element in which resistance varies as a function of temperature. Also, we have the heat-sensitive cable detectors. It consists of two current-carrying wires separated by heat-sensitive insulation that softens at the rated temperature, thus allowing the wires to make electrical contact. Also, we have the liquid expansion detectors. It has a sensing element comprising a liquid that expands with an increase in temperature. Okay, so take note, fixed temperature heat detectors are more suitable for property protection rather than life safety application. So the second type is the rate of rise heat detectors. It signals an alarm when the temperature at the detector increases at a rate exceeding a preset value. Types of rate of rise heat detectors. We have the pneumatic rate of rise detectors. It has an air chamber with a diaphragm enclosing a portion of the chamber. As the detector is exposed to heat, air within the chamber expands. Then, process follow until the diaphragm expands. It completes the circuit within the detector and initiates an alarm. We also have the electrical conductivity rate of rise detectors. It has a sensing element that changes its resistance with a change in temperature. So third type is the flame detectors. It optically sends high levels of either infrared radiation or ultraviolet radiation. Combination of ultraviolet and infrared detectors are also commercially available. These detect specific wavelength ranges of ultraviolet or infrared radiation and send an alarm signal. Fourth type is the ionization smoke detectors. It is designed with a sensing chamber that has a radioactive element. Smoke particles then entering the sensing chamber change the electrical balance of the air. It responds first to fast flaming fires. The fifth type is the photoelectric smoke detectors. It uses a light scattering or light obscuration principle. When smoke particles enter this chamber, they interfere with the beam and scatter the light. A photodiode monitors the amount of light scattered within the chamber. When a preset level of light strikes the photodiode, the alarm is activated. This responds first to slow smoldering fires. The sixth type is the air sampling smoke detectors. It uses a similar approach to light obscuration detectors. However, a laser or xenon tube is typically used as a light source. In addition, dust particles from air samples then enter the detector. These samples are exposed to a light beam that bounces light off small particles released by the combusting materials in the protected area. The scattered light is converted to an electronic signal and passed to the control system. This system can be designed to be 1,000 times more sensitive than standard ionization and photoelectronic detection systems. Also take note, heat and smoke detectors are located on ceilings and walls in the spaces they protect. Placement and spacing is determined by ceiling configuration and projections that impede flow of smoke. Other factors include airflow rate, elevation, humidity, and temperature. We also have what we call the manual pull station. These are lever-like devices mounted on a wall or pole in strategic places in the building and that are connected to a building fire alarm control panel or directly to the municipal or district fire alarm system. When the pull station lever is pulled, an alarm is sounded. Alarms. It is an audible evacuation signal delivered through bells, horns, chimes, buzzers, and sirens. Strobe lights are used in combination to ensure that hearing-impaired occupants recognize the need to evacuate. Emerging voice communication systems. It provides pre-programmed recorded messages that offer direction, instructions, and a calming voice in an emergency situation. These are automatically transmitted to speakers located throughout the building. It can also be provided with a two-way communication subsystem which enables responding firefighters and other emergency personnel. Fire detection and alarm systems include a system control unit, a primary or main electrical power supply, a secondary standby power supply, alarm initiating devices, alarm indicating devices, ancillary controls, remote alarm indicators, control circuits. Fire System Control Unit. This serves as the center of the fire alarm systems, while Fire Alarm Control Panel. This is the central part of a fire detection or alarm network. Fire Command Center is a remote panel or set of panels connected to the fire system control panels. It is typically located at an entrance of the building in a space with a minimum 1-hour fire resistance rated construction. It includes the following: voice fire alarm system panels and controls, fire department two-way communication service panels, telephone for outside communication, sprinkler valve and water flow status panels, smoke management controls, elevator location status panels and annunciators, fire pump status panels, and emergency generator status panels. So how does fire alarm control system works? First, its operation begins with the smoke or heat detector sensing a fire and sending a signal to the control panel. At the control panel, the signal is processed. Depending on smoke levels and the pre-programmed alarm levels, the appropriate output signals are generated. So we have the 3-stage alarm levels. The first stage is alert, indicate that the system has detected something out of the ordinary that should be investigated. Second stage is action, indicate that a potential fire exists and that emergency procedure should begin. Third stage is fire, signifies an actual fire condition. So building security in general includes consideration for initial building design, material selection, building security systems, perimeter protection, interior protection, video and audio surveillance, control panels and centers, alarms, electronic access control systems, security personnel, emergency power systems, emergency lighting, as well as emergency plan action.